So we will try to understand the AES algorithm, and we know that AES is a symmetric key algorithm, right? So it's a symmetric key encryption. So in a symmetric key encryption, and in particular the block ciphers which AES belongs to, you have got like your plain text or the inputs in blocks, and that is encrypted by this encrypting algorithm which is called as AES, and there is a key, right? Here this is your secret key, which is shared between the sender and the receiver. So the sender and the receiver have got the same key, and like it's the same key which is used both for encryption and for decryption. So now in this class of algorithms, so the decryption also needs to be defined, because this has to be a reversible process, because from the cipher you should get back the plain text by applying opposite operations, and it again operates on the same key. The encryption and the decryption both operates on the same piece of key. So now let's try to look at inside the block cipher, the structure of the block cipher. Okay? So inside the block cipher, you will see that it is made up of several rounds. Okay? And therefore, these algorithms are also called as iterative ciphers, because you are iterating certain rounds again and again. So you can see round 1, round 2, maybe round n. Okay? And every round requires a piece of the key. So you can see that there is like a round key that is being provided as an input to each of these rounds. But the original keying material is your input secret key. So it could be maybe a 128-bit key, or maybe a 192-bit, or maybe a 256-bit key in case of AES 128, 192 and 256. So then these round keys are derived by a specific algorithm which is called as a key expansion algorithm. Okay? And it is also called as a key scheduling algorithm. So this essentially is utilized to obtain the round keys from the original secret key. So you basically take the secret key, get the first round key, from the first round key you get the second round key, and so on. And every round key is used in the round operation. Right? In case of AES, the round key has a specific property, which is that this key expansion is reversible. That means, like from the last round key you obtain the previous round key, from the previous round key you can obtain the previous to previous round key, and that way you can obtain the original secret key also. It is a very like a very systematically developed easy function which you can also reverse. Okay? So the reason why probably AES made such kind of constructions is because they wanted to make it amenable to implementations. Okay? They wanted to ensure that the algorithm can run with a good performance on simple microprocessors, which are like very low cost and maybe 8-bit microprocessors. Okay? And that is why you will see that the AES algorithm is often defined in bytes, in chunks of bytes, because it runs nicely on 8-bit microcontrollers. Okay? So now let's try to see what happens inside. So as I mentioned that typically your key length can be 120, 192 or 256, and inside the encryption round there are certain operations which are very important for the overall security. Okay? So you will find out that inside the cipher there are certain constructions which are called as substitution boxes. Okay? So these substitution boxes are also abbreviated as S boxes. Okay? And there are certain other layers which are called as diffusion layers. So these two are vital components of a block cipher. So the substitution boxes or S boxes provides a very important property to the cipher, which is called as nonlinearity. Okay, which means that, see, a cipher, right, a good cipher cannot be a linear cipher. Why? Now because that would mean that if it's a linear cipher, then if I give you like the one plain text and the corresponding cipher text and another plain text and another cipher text, from there you can extrapolate and get all the other possibilities, right? So a good cipher should be nonlinear, and in particular it needs to satisfy two properties. One of them is called as confusion and the other one is called as diffusion. So confusion basically is a property which hides the relation between the cipher text and the key. Okay, so if I give you the cipher, From there, it should be difficult for you to understand what is the key. And the property which hides the relationship between the ciphered and the plain text is called as diffusion. Okay? So these are two important definitions which were originally gave in the very classic paper from Shannon, okay, way back in 1948, where he told, like how to construct a good symmetric key cipher. So the number of rounds of the cipher is defined, like by a very, very rigorous analysis, which are called as cryptanalysis. Okay, and the idea being that even if I give you a plain text and if I give you a cipher text and I give you lots of them, okay, you should not be able to tell me what is the secret key with which is with an effort which is lesser than its brute force complexity. Okay, so what is a brute force complexity? So if I give you a 128-bit key, then its brute force complexity is 2 to the power of 128. If I give you a 192-bit key, then it is 2 to the power of 192. Okay? So theoretically, any attack which is complexity less than 2 to the power of 120 is a break. Okay? So if I give you an algorithm which tells you the AES key with a complexity of 2 to the power of 127.6, that's a break. But not practical, because 2 to the power of 127 also is a very large number. Okay? 2 to the power of 80 is probably more than the number of particles in the universe. So you can imagine that 2 to the power of, like 80 is such a, beyond that numbers are so big. Okay. So these rounds of ciphers are very carefully determined, and in case of AES, as we know, in AES 128, the designer said 10 rounds are good enough. Okay. 20 years of cryptanalysis, still we don't know a better cryptanalysis than a brute force search. So it's a very well designed algorithm. So this brings us to different classes of attacks, and I mentioned that what I just now was talking about are called as cryptanalytic attacks, where you just have the exposure of the plain text and cipher text, and from there you try to recover the key. But in real life you can do much more things. Okay, as I was mentioning about side channel attacks and so on, there you have got additional information which you try to exploit and get the key in practical terms. So let me, quickly talk about the AES algorithm, but I believe that you know the Kharagpur's principle, right? Yes, no? Okay. So in that case, it's good to state this. Okay. So the Kharagpur's principle tells that we don't believe in security by obscurity. Okay. We don't believe that the fact, I design a crypto algorithm and then I don't tell anyone, I hide the algorithm, okay, nobody will know the algorithm. That's a bad ploy, because history has taught us that if you keep the algorithm secure and so on, eventually it will break because a human can be compromised. Okay, just now in the slide you can show, like that if I take a gun and hold it against somebody, right, that person will tell the entire algorithm. And then, there is a chance that algorithm is very bad, okay, a weak algorithm, and that will be broken. So rather, the better ploy that we try to adopt is that the cipher is published. Everybody knows the cipher. Even the adversary also knows the cipher. Like you know the AES algorithm. I know the AES algorithm. Anybody who is reading the book knows the AES algorithm. So where is the secret? The secret is in the key. Okay? That means the moment I change the key, right, my previous knowledge doesn't work. Okay? So that essentially is a very nice, if we say security by design, not security by obscurity. So now let us, I will try to talk about AES in very briefly, and I will probably skip few things from here and talk about this. So AES essentially, as we know, is a block cipher that was standardized by NIST from 2000, and it has got few important components, and that is something that we will try to understand now. Okay. So it comes up with a confusion layer, a layer which gives confusion, which is called as the sub-bytes, okay, or a byte substitution layer. So you can see here, I write down each components of the round. So what we do in AES is we take a plain text, we perform an XOR with a key. Okay, so this plain text is 128 bits, and the key is also 128 bits. Okay, so you do first an XOR between the plain text and the key. and then you like make it pass through certain transformations. So which we called as the rounds. Okay, so these are the rounds. So these are the rounds of the cipher. Okay. So now we will try to see what happens inside these rounds. What are the blocks inside these rounds? So this brings us to two important layers. One which is called as a confusion layer, which gives us byte substitution. Okay. Another is called diffusion layer, which essentially gives us diffusion. So typically here the two important components are what are called as shift row and mixed columns. Okay, so these are certain things that we need to understand how the later on discussions or the attacks work. Okay, so let me just quickly ask, did you already go through this material, like about what are the internal rounds of AES? No, right? So then I'll take some time to go through it. So in this case, like the first, so we'll try to understand what is AES, okay, and how it is made of. So in general, like AES was designed by two Belgian mathematicians or cryptographers, Vincent Riemann and Johan Demen. Okay, and therefore in their name they call it as Rindal. So Rindal was the name of the original cipher, and there were many other competitors also, like Serpent, Two Fish, Mars, RC6. But in that competition, overall Rindal got the highest marks. But you can observe here that there are many reasons why Rindal won. So it is not only security, because in terms of security, Rindal was probably not the best marks. As you can see, there were some other algorithms which got higher marks. But there were other things, like in particular software performance, hardware performance, on which Rindal scored and got higher marks. Okay? So overall Rindal won, and it became the advanced encryption standard. And from 2000-2001, it is a de facto standard block cipher around the world. Okay? So therefore now let us try to see what is AES. So the AES state is represented in the form of a byte. Okay? So that means it is a byte. So it is very, as I mentioned, like AES works very nicely on an 8-bit microcontroller. So it is described in terms of bytes. Okay? So if I look at this and say that this is a byte, and the AES plain text data has got 128 bits, so how many bytes should it comprise of? 16, right? So it is actually made of 16 boxes, but 16 bytes are organized in the form of a 4x4 matrix. Okay? So this is how the AES is described. The AES state is described. So let me write down this and say that this is the state. So likewise, your key is also, you can imagine that as a 4x4 matrix of where every element is a byte. Okay? So you feed this plain text to the input of the AES, you give a similar key, and it should result in a ciphertext which also has got 128 bits. So you can also imagine that as 4x4 matrix where every element is a byte. Make sense? So it is basically a 16 bytes arranged in a 4x4 matrix of bytes. Okay? So now let's try to see what happens inside. So in AES 128 algorithm, you have got, as I mentioned, the first thing that you do is an XOR with the key. Okay? So this step is also called as add round key. So you basically take the round key and you XOR. So and the addition is in this case what is called as XOR. Okay? So you basically like take every bit of the plain text of the state and you combine with the key. So XOR, I believe all of you know the XOR mapping, right? So XOR is nothing but a simple mapping where you have got two inputs A, B, and A XOR B is defined as 0, 0 will give you 0, 0, 1 will give you 1, 1, 0 will also give you 1, but 1 and 1 will give you 0, right? This is a simple XOR transformation. right? So the XOR has got a very nice property, actually many nice properties, okay? So one of the nice properties of AES is you can see that it is a balanced function. That means the number of zeros and number of ones in the output are same, okay? If you see the AND truth table, it is very much skewed towards a 0 or a, like the odd truth table is skewed towards a 1 and so on. But an XOR truth table is nicely balanced. The number of zeros and ones are exactly the same, okay? Moreover, it's also a reversible process. You can see this, that if I give you A XOR B and if I give you B, from there you can obtain A, right? You can just do a XOR between these two given input columns and you will get the other one, right? What I mean is that if you say that this is M and this is K and you get M XOR K and call it as the M dash, from there you can obtain M, or you can obtain M by just doing an XOR with M dash and K, okay? So it's a reversible process, okay? So that is why people like the XOR operation for mixing the key. Why? Now because if you know the key, right, and then if you observe the output of this addition round key, right, then you can remove this and get back the original data. So you can use it nicely for decryption, right? So now there are following other steps also. For example, as I was mentioning, you have got byte sub, shift row and mixed column. So I will quickly talk about this, okay? So what is a byte sub? So byte sub is essentially, like an operation which does byte sub, okay? So it basically substitutes every byte. So what I mean is that if you see this, like the state matrix of AES, this is your state matrix of AES, right? So what I will do is I will take every byte, say I will take this byte, and I will pass it through some kind of lookup. So what the lookup will do is will give me an output which I will just substitute at that location, okay? So I will just substitute at that location. So I will do a substitution byte by byte. That is why it is called as byte substitution, okay? So therefore, right, for the 16 bytes, how many S boxes do I need? How many lookups do I need? 16 lookups, right? And every lookup, you can think of that to be a table which takes a byte and replaces it by a byte, okay? Very simple. So the next thing that we will also study is what is called as shift row and what is called as mixed columns. Now these two layers or these two blocks are there for diffusion, which means that if there is a disturbance in the state matrix of AES, then we will see that how these two layers nicely combine to spread diffusion inside the cipher, okay? And they are very nicely designed to ensure that your cipher has got sufficient diffusion properties, okay? So I will talk quickly about that. So let's see. So likewise, you can also define your inverse operation, which means that you can start with the cipher text and walk back and get the original plain text, okay? So this, I just leave it to you, maybe you can think about this, but the idea would be that every layer has got an inverse operation. So now let us try to see, like what it is really speaking, okay? Right now I was largely doing hand waving probably, but now we will try to little bit get into the details of the AES algorithm, okay? Any questions so far on the AES algorithm? So for this, we have to little bit understand the mathematics of AES, okay? So AES is actually made up of a specific, like field, which are called as binary finite fields, okay? Or they are also called as Galois fields, okay? So in this case, what it means basically is that it is also often represented as GF 2 to the power of m. In the case of AES, we have got GF 2 power of 8, okay? So remember that I was talking about this state matrix where there were 16 bytes. Each of these element is a member of this GF 2 power of 8, okay? So what essentially does it really do? So we know that if there is a finite field, okay, I need to kind of define a mathematics wherein I can take two elements from this field and I can perform various operations. Okay. I can perform addition, I can perform multiplication, and so on. So what I will be doing here is I will be trying to see how AES is defined, or how is this rather binary field defined in the context of AES. Okay. So one way you can think of is, the way you can think of is, in this particular field, this is like how is an element represented. Okay. So what you can do is, you can imagine that any element here, say I called it as the first element, if I write down this as A, suppose this is an element from this field GF2 to the power of 8, you can conceptualize that as a byte. Okay. So you can conceptualize that to be a byte. That means it's an 8-bit string made of zeros and ones. Okay. Likewise, there is another way of representing this also, which is called as a polynomial representation. So what I can do is, suppose I have got a string, let me just quickly write it down, say 1, 1, 1, 1, maybe 0, 0, 1 and 0. Suppose this is my 8-bit string. Okay. So there is an equivalent polynomial representation also. Okay. So this is a polynomial. You can also represent this as a polynomial. So this polynomial would be like that, this is nothing but x plus, maybe this is like the coefficient of 1, this is the coefficient of x, this is x squared, this is x cubed, this is x4, x5, x6 and x7. So this will be nothing but x plus x power of 4 plus x power of 5 plus x power of 6 plus x power of 7. So you can also conceptualize this to be a polynomial. Okay. So therefore I can choose different elements from this finite field and I should be able to do certain operations. Okay. So in particular, the operation of interest at this point will be two operations. One is an addition and the other one is a multiplication. Okay. Because I need to define the properties of a field. Okay. And for this I need these two operations. So it turns out the addition is very easy to define. What I can just do is I can do a modulo 2 addition, which is nothing but an XOR. Okay? And that is why the XOR that you see in the AES description is nothing but a Galois field addition. You can take two elements, AX and BX, and you can define their addition, which is nothing but a bit by bit modulo 2 addition. Okay? So this is kind of easy. Like what I mean is, if I want to do x plus x, this is not really 2x in the normal algebra that probably I would be doing. But here in this representation there is specific context of what this addition means. Okay. So what we will be doing therefore is this, that is like if I maybe I'll just quick little bit go ahead and talk about this.